Anyone else? 민영 학생 말고 또 없나요? 네, 현빈 학생은 battery, right? Okay, battery material, right? Lithium-ion batteries, organic batteries. Okay, I think we'll definitely talk about a bit of battery. But I believe, Hyunbin, you are from energy department, right? So maybe, perhaps you can give us a better lecture than myself. But yes, we'll cover the battery. But thank you, Hyunbin. 그럼 제가 좀 이름이 상대적으로 좀 생소한 학생들, 아마 학부생일 것 같은데, 다희 학생? 왕다희 학생? 네, is there any topic that you want to learn? 그냥 편하게 얘기하셔도 돼요. 뭐 배우고 싶은 topic. Okay, so you want to learn about sensors. Okay, perfect. So there are many sensing mechanisms: physical, optical, chemical, thermal, right? And yes, I'll definitely talk about the sensors. Yeah, so thank you. Okay. So currently there is 45 students in this classroom right now. And I would love to ask questions, but there are too many people. So yeah, I mean, I'll stop here and thank you for Minyoung, Hyunbin, and Dahi for sharing your opinion. Okay? Okay. 뭐 사람이 너무 많아서 어떻게 수업 중간에 출석 체크를 할 수 있을지도 모르겠네요. Anyways, okay. I have a sore throat. 제가 목감기가 걸려가지고 I may have to speak very quiet. 뭐 ASMR 정도는 아니지만 좀 조용하게 얘기를 해야 돼가지고요. 좀 이해를 해주세요. Okay. All right. So today is the third lecture. We'll talk about the nanoscale effect. So we learned about this scaling law in the last lecture. We learned how things behave when it scales down, or how those physical phenomena changes as a function of dimension, right? Something is important in one dimensional. Something is important in terms of area. Something is important in terms of volume. So all these different properties or different phenomena changes as the dimension change. So today I will learn about the very good example of this nano effect, and more of a fundamental, more of an introduction, very brief explanation of how this nanoscale effect takes place in liquids and also in heat. Okay. All right. So nanotechnology and liquid, right? So when we talk about this liquid, okay, I mean, of course, there are many important properties of liquid, right? I mean, when we talk about liquid, maybe we can say, maybe you are saying, oh, is liquid transparent? Is it opaque? You can also say whether it is viscous or not, right? Honey is viscous. Soju is not viscous, right? Okay, right? So when you talk about these liquids, there are a lot of these things, right? And also the very important thing, the very important property of the liquid is the surface tension. Okay? So what this surface tension is, right? I believe everyone know the terminology surface, and I believe everyone know what tension is. So when we say surface tension, it is the elastic tendency of a fluid surface to achieve minimum surface area as possible. Right? So when you drop, so let's say this is your desk, okay? When you drop a liquid, right? you get this circular shape, right? It is not like, or you get something like that, all right? So you have formation of certain surface, okay? So this shape of surface or the size of the droplet, all right, depends on the surface tension of the liquid, okay? So let's say when we go to bar, right, after maybe we are in the second week of school, so if there are any undergraduate student in campus, maybe they'll go out for soju tonight, right? So let's say you have a glass of, okay, soju-chan, okay, and let's say you pour a soju. So for Manisha and some other international student, soju is the one of the most popular liquor in Korea. So we pour soju, right? Right? And when you pour so much, you get this meniscus, right? When you see from the side, you have this liquid, right? It's 찰랑찰랑, 그죠? Liquid is above the top of this glass, but it doesn't go over, right? Right? There is this formation of this liquid meniscus, and this is also because of the surface tension. Okay. So when we talk in the bulk of liquid, each molecule is pulled equally in every direction by neighboring liquid molecules, resulting in a net force of zero. So when you see a liquid molecule here, there's a liquid molecule here, 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 here. There's everywhere. Right? So they are exerting or they are pushing at the same magnitude at different directions. So when you add all these vectors, right, the net force is zero. Okay? That is why the liquid is still. The liquid does not move in bulk unless there is external force acting on it. Okay? However, the molecules at the surface do not have the same molecule on all sides of them and therefore are pulled inwards. Okay? Okay. So it's the case for, sorry, case for this, right? This creates some internal pressure and forces the liquid surface to contract to the minimum area. So this unbalanced distribution of force induces the internal pressure and forces liquid surfaces to contract to the minimum area. Okay? So when you put something very light, it floats because there's internal pressure acting on the surface of the liquid. Okay? So this type of surface tension is also related to the capillary force. Okay? Excuse me. Oh, I'm sorry. 이어폰 끼고 계신 분들한테 죄송합니다. 제 기침이 너무 크게 들릴 것 같은데 죄송해요. Okay? So, when we talk about this pressure in nanobubbles or droplets, there is a famous equation I'm sorry, I turned off my tablet. Alright, I'm sorry. Relates the pressure drop to the surface tension and the dimension of the bubble and droplets. Okay. So when we talk about droplets, okay, for droplets, the change in pressure between this internal pressure and this outside pressure, right? This internal pressure should be higher, right? This delta P is 2 times surface tension divided by the radius of this droplet. Okay. And for bubbles, the quantity is doubled. And you may think about it, the shape of bubble right, is basically twice the volume of this droplet. So you'll have 2 times the amount of surface for bubbles compared to the droplet, right? That is why this pressure gets doubled. Okay. So you can say, okay, I mean, yeah, there are some pressure difference inside this liquid and air. I mean, that is fine. So what? Why does it matter? Right? Again, such effect in liquid its property heavily depends on the property called the surface tension. It has the terminology called surface, right? And we know that we have learned that in nano, surface to volume is really, really big. So this effect of surface becomes really big for this liquid. So let's say if you have 50 nanometer liquid bubble or droplet, right? Just like a 뭐야 식물 세포 같은 거 보면 세포라 그러나 이렇게 뭐 이렇게 봤죠 옛날에 그죠? 수업 시간에 뭐 양파 껍질 같은 거 그죠? 이렇게 까가지고 현미경으로 보고 중학교 때였던 것 같은데 그죠? 이쑤시개로 입 안에 긁어가지고 입 안에 있는 거 막 보고 그랬죠 그죠? Right? So when this thing's droplet becomes really really small, the pressure inside is as high as 400 kilopascals. That is 4 times the atmospheric pressure, which is 101 kilopascal, right? Okay. So what we are saying is that when the liquid or droplet becomes really small, it can store a very high pressure. It can endure a lot of pressure. Okay. Okay, so that is one example of liquid and nanoscale. All right. So okay, more about this surface tension. In every case, creating surface costs energy. Okay. So I have tablet today, so I'll be more creative. So let's say you bought this big steak. Right? Very good, right? If you cut it with a knife, this is knife, right? What you are doing is you are creating these surface. right? All right. So in any cases, creating surfaces costs energy. Okay. The surface tension, the surface tension, right, has the unit of newtons meter. Okay. So it is basically a required force to generate a unit length of a certain surface, or if you change this unit length into surface, if you multiply this by dimension L, right? Force times, right? Distance is energy, right? Unit length, meter times length is surface area, right? So it can be reconverted into energy over unit surface. Okay. So by slicing this block in half, you get this new surface, right? And this new surface is 2 times V. So when you create this, it'll be energy is area times surface tension. Okay? Okay. So you'll end up with the in case of force times distance. And this is the definition of work or energy, right? So here is the relation. So so the reason I'm talking about this liquid and surface energy or tension in nano class, right, is because you need to understand these very fundamentals to understand what is exactly happening in nanoscale. Okay? So now we know this term, surface tension. Okay, so that is great. So now we have talked about the pressure inside this liquid, and we talk more about the surface tension. Okay, or surface tension or energy required to create area, certain area, right? Good job, right? So now we have this idea. So we can actually quantify, we can actually calculate, or we can actually measure this surface tension or this energy required to create a certain area by measuring the contact angle. So let's say in life, so let's say this is your desk. If you drop if you drop honey, right, honey will form this kind of droplet, right? But if you drop water, let's say they are same volume. So depending on this liquid type or liquid property, their the amount they get spread out changes. And we can measure this, we can actually quantify this by measuring this angle right here, which is the angle at this contact here. Okay. So if you take this out, If you take this out, all right, it can be like, oh, there's this table, and there's this droplet. So this is liquid. This is solid. And this is vapor or gas. So at this interface right here, you have a region where liquid, vapor, and solid is meeting, right? And when you actually measure the angle right here, this is contact angle. Okay, so let's say this is the surface tension or the interfacial energy between solid and vapor. So this is the energy required to create a unit area of surface between solid and vapor medium. 그러니까 고체와 기체 사이에서 어떠한 면을 만들 때, 그죠? 여기죠, 여기, 그죠? 필요한 에너지입니다. 자, 여러분이 이렇게 공중에 팔을 들고 있으면 여러분의 피부와 공기가 맞닿아 있죠, 그죠? 여러분의 피부의 면적만큼 surface 지금 텐션이 있는 거예요. 그죠? 근데 우리는 그걸 느끼지 못하죠, 그죠? 팔을 움직이는데 별로 어려움이 없죠, 그죠? 근육이 있다면, 그죠? That means the surface tension between solid and vapor is usually very small. Okay? Okay. And SL is symbol for the interfacial energy between solid and liquid. And this is just between the liquid and vapor. Okay. 여기가 물이 맞닿아 있는 데가 SL이고. Okay. So when you actually there's this fine equation called Young's equation, which relates this angle with all these three terms. That is cosine theta is interfacial energy solid vapor minus solid liquid over the interfacial energy of liquid vapor. Okay. Okay. So for the same type of surface and same type of vapor, and for a certain type of liquid, this angle right here is fixed. Okay? And in many cases, the many surfaces that we use, metals, woods, plastic, right? Many of them usually have this contact angle smaller than 90 degrees. Okay. And what that means, I'll get into more detail. Okay. So whenever a surface makes contact with liquid, we call that surface is wet. Okay? 젖어 있다, 그죠? And in nature has provided some water repelling examples from which we can learn. Okay? So being wet is good sometimes, right? If you have to draw something using paint, or if you want to make something wet, then it has to be wet, right? So it has to be water friendly, right? Water has to stay in that surface, right? 그죠? 뭐 젖어 있어야 되는 경우도 많죠, 그죠? Right? But in many cases, sometimes, in certain situations or in certain systems, we want that system to be water repellent or water repelling, 젖지 않는. 뭐 예를 들어서 our umbrella right? Our raincoat, our shoes, right? It'll be great if it does not get wet. Our glasses, 안경, 뭐 젖지 않으면 좋겠죠, right? My hair, it'll be great. It doesn't get wet. Actually, it has to be wet so I can shampoo every day, right? But there are some cases, right? So if you look at here, the bird feathers, lotus leaves. 새털이라고 하나요? 깃털이라고 하나? 새털이란 말이 있나요? 지은 학생, 새털이라는 말이 있나요? 깃털? 아, 오케이. 네, 오케이. alright. 예. 넘어가 주세요. 오케이. alright. So 깃털. 네, 깃털. 오케이. 저 참고로 한국 사람입니다. 군대도 갔다 왔어요. Okay. Alright. And lotus leaves is 연꽃잎. Alright. Water walking insects, 그죠? 소금쟁이, 뭐 얘들, and some types of spiders. Okay, they are all water repellent, right? In nature, right? Bird, they need to make sure their body doesn't get wet, so they can fly while it's raining, right? Or they can fly right away. Lotus leaves or many leaves, right? It has to be water repellent, right? So it does not get wet. So it can do this continuous photosynthesis when there is a sunlight, right? So we have seen this type of thing in nature. Okay. So in wetting, there are many cases. There is a case for flat surface, and there is a case for rough surface, right? And some surfaces, they're perfectly flat, right? But actually, when you go in, and this is the equation that we have learned for the flat surface, right? But when you go to the rough surface, or when you actually look at every surface with a microscope, they all have a certain roughness. Okay. So there are some cases where the surface is rough. 여러분들이 지금 like a cell phone glass, cell phone monitor. 그죠? 유리도 있고 굉장히 플랫해 보이지만 if you look at that glass in your cell phone under the microscope, it'll have a very it'll have like size roughness, right? But you cannot really feel it, right? Because our human touch sense is not sensitive enough to tell the difference of this height difference, right? Okay. So anyways, many surfaces have roughness in nano scale, or you can make it intentionally rough in whatever scale you want via manufacturing process. Okay. So when surface is rough, the new model, called Wenzel model, and also there is a Cassie model or Cassie-Baxter model kicks in. So we'll learn about these two in more detail in the case. But to give you a short preview, right, for this case where the liquid makes the contact with the entire surface of this rough structure, we need to consider the surface roughness into account. Okay? And this is surface roughness is the ratio of the actual to the apparent surface area of the substrate, right? So if you look at from the top, 이게 사람 눈이에요, right? Then this is the area. But in reality, if you look at from the side, you can now see this roughness. So you can be like, oh, the actual surface is higher than that of the apparent surface area. So for roughness is always higher than 1. And when roughness is 1, then it is perfectly flat. Okay? Okay. Right. So, Wenzel model. Again, we know this equation, right? R is the surface roughness, is the real area over projected area. And we have this equation like this above. If you rearrange this equation, what you are getting is cosine zeta equals surface roughness times cosine zeta 0. And this 0 is the contact angle on flat chemically same surface. Okay, so here you get new angle called zeta, okay? And this value is different from the original angle when roughness is not equal to 1. Okay, so using this model, right, you can predict the contact angle of this structure, or and vice versa. What you can do is if the surface is hydrophilic, roughness makes the surface to become more hydrophilic, right? And if the surface was originally hydrophobic, all right, when the contact angle is higher than 90 degrees, Celsius 아닙니다, right? It's not Celsius, it's angle. Roughness makes the surface to become more hydrophobic. Okay. So this is good. This means that, oh, by controlling roughness, we can control contact angle. Okay, that is good. Sorry. And then there is also a case a wetting of chemically heterogeneous surfaces. In the case of a flat chemically heterogeneous surface, the wetting can be described by the Cassie approach. Okay. For a two-component system, the wetting is described by. So I mean, before I go in, what it means is that in many cases, so this is solid and this is gas. Okay. In many cases, when this roughness is too small, when we put droplet on it, because of the surface tension of this droplet, okay, the internal pressure is not high enough to break this meniscus right here. 영작생, 네, okay. So there was a question from 영작생. She asked, like, Professor, can we control the surface tension? So to give you an example, so give out my answer first. The answer is no, right? Surface tension is the material property. Okay? surface tension 값을 인위적으로 조정을 하는 게 아니고요. 네. 구조의 변화나 구조의 디자인을 통해서 그죠? 기존에 가지고 있는 surface tension을 그대로 이용하되 물방울이나 액체가 얼마나 많이 젖고 덜 젖고를 컨트롤할 수 있다는 얘기거든요. Okay, so my answer is that again, surface tension is material property, and what I'm trying to say is that by creating very small scale roughness, we can change how this liquid behaves on surface or how it gets wet on a surface, even though that liquid maintains the same liquid tension, same surface tension. Okay? 네. 설명이 좀 미진하면 수업 끝나고 저한테 전화를 주셔도 돼요. 그럼 제가 그 목소리로 좀 설명을 더 추가로 드릴게요. Okay? Alright, so I think everyone is fine, right? Okay. So in many cases, when this roughness is very small, this droplet somewhat floats on this structure. So when you consider this bottom surface, some portion of bottom is in contact with solid, some are in contact with gas or vapor or air, right? So we have to take account of this vapor effect. Okay. So if you look at here, for a two-component system, the wetting is described by cosine the new contact angle is equal to F1 theta 1 plus F2 cosine theta 2. Okay? Where F1 and F2 are the area fractions of the material. So how much in percentage, right? Oh, F3 is taking 30% of this bottom surface, and F2 is taking 70%, right? Then you have this fraction. And theta 1 and theta 2 is the contact angles of pure materials in a perfectly flat condition. Okay? So you can get these two values of theta 1 and theta 2 using okay. Okay. So by making this artificially roughened surface using this nanotechnology, we can make a very different um, surface structures. Okay. So if I share my screen for real quick, okay, give me a second. 잠시만요. Okay. So in reality, there's some delay because of this internet connection, right? But in reality, in a Casey-Baxter model, in real world, surface roughness induces the contact of a droplet with air and solid. Okay? In such case, air is air is assumed to be entrapped in the voids of a rough hydrophobic surface. Okay? Okay. So in reality, if it's perfect solid, it's higher than 90 degrees. Yeah, but in air, the contact angle of liquid and air is 180 degrees. What it means is, in air, the liquid will form a perfect droplet here, like this, right? Okay, so we can rewrite this equation as cosine 180 is minus 1. Okay, so you get this relation here. Okay. So the reason I'm spending 45 minutes in the liquid in nano class is that people can make these physical nanostructures to change how liquid behaves on these surface. Okay? 즉, 나노 구조물을 어떻게 만드냐에 따라서 표면을 굉장히 물에 잘 적게도 할 수 있고 혹은 표면을 액체에 굉장히 안 적게 할 수도 있습니다. Right? Then you might be thinking like, okay, why does this matter? Why? Think about that you can make this nano microstructured surface, right, to make it liquid repellent, right? If the window does not get wet, okay, then you do not have to really wipe the window. The liquid droplet will just drop off, okay? So in reality, when you buy a car and when you wash it, there is an option that you can add a layer on your windows. 광택뿐만 아니라 you have an option to add a film to make it more water repellent, so you can see better in the sun and when it's raining. Okay. Also, when there is a large temperature difference, especially when there is a cold surface in a hot medium, there is this condensation, formation of liquid droplet. Okay, this is because this air molecules in gas form, when they make contact with this cold substrate. Okay, so let's say this is a cup, cold cup. Okay, but let's say this is air molecule. Okay, they're gas. When they get near to this, and they're hot. When they get near to this cold cup, this cold will take away a lot of hot energy, right? So these molecules will lose energy. And we learn from middle school science or high school, right? When the molecule in gas, if its temperature drops or when it loses a lot of energy, it becomes into the liquid form. Okay? So there is this condensation. 뭐 한국말로 하면은 뭐 결로라고도 하죠, 그죠? Okay, okay, right? So if we make this pipes or the wall become water repellent, there is this no formation of liquid. Liquid will just slide and drop. Okay, so this means that we can make this system to be water repellent. And also this is submarine, right? If we make this surface to be hydrophobic, right, then that means the friction will be very small, which means we can save fuels. Okay, so there is a lot of application. Okay, all right. Any questions on a liquid part? 질문 없으세요? 장현우 학생 질문 없나요? 아, 네, 감사합니다. 네, 명지 학생 여기서 본인이 okay, so 명지 is asking some questions in Korean, so she's asking that can we change the angle by changing the surface structure? So her question is, are we controlling the how the liquid behaves, not the actual surface tension? My answer is yes. Okay. I'm not sure what this R is. Is this surface tension or the radius or roughness? But yeah, I mean, so the surface tension is the fixed material property. Okay. I mean, yeah, so before Sugato, I'll talk to Youngji. So, okay. So yeah, it is a fixed value, right? And when its material property is fixed, we cannot really change how it behaves, right? If a certain surface is very high energy or is very hydrophilic, then we cannot change how it behaves, right? But if we put nanostructures or nano roughness on that surface, we can change how it behaves, not its surface tension. So surface tension is a fixed value for a certain material, but we are changing how it behaves. 그래서 명지 학생이 이해한 게 정확해 보입니다. So back to Sugato, I mean, it depends, right? In some, okay. So for your first question is that, I mean, it depends on your use. Some cases, the smooth is better. Sometimes it's rough is better, right? So it totally depends. Sometimes you want the surface to be hydrophilic, or sometimes you want the surface to be hydrophobic, right? So I cannot really tell which is better, but for specific application, it depends, right? And you said how to determine the contact angle in any smooth or rough surface. Okay. So let me actually check, Google this for you. Okay, thank you for all the questions. Okay. Okay. So if you look at here, so this is the tool, right? So this is the tool, for example. What it does is that you place your sample on a flat surface, and you can place your sample here, right? It can be smooth or rough or whatever surface that you want to use. And you put the liquid that you want to use, right? And then you drop the liquid and you take image using this microscopic camera, right? So yeah, so and what it does is that you'll get a measurement like this. Right? When you drop the liquid, you are taking the image from the side, and you are seeing, oh, and you are measuring this angle here. Uh, it's a very simple microscopic tool, and at DGIST we actually have a very nice this contact angle measurement tool. 한국말로 하면은 뭐 접촉각 측정기, 계측기라고 하는데요, right? So we have this tool in our campus, so we can measure using this tool. Okay. Okay. So actually, okay. Let me ask the 수가트 first. 질문 다들 감사합니다. 현빈 학생 잠시만요. So when you So using this type of tool or using a very high speed camera, you can actually capture type of movement. So this is a very, very good example here. Let me actually download this thing. 죄송해요. 제가 좀 즉흥적이어가지고 좀 이렇게 좀 그럴 때가 있어요. 죄송합니다. Okay, so let's look at this example here. Okay. We have a jumping droplet, okay, which looks really cool. This is great. Okay, but you see that there is a jump when right? There's a jump when right? There is a jump when these two droplets merge. This means, a jump means when we make something to move or jump, this jump requires energy, right? Okay. So can anyone guess where this energy is from? 네, 민영 학생, 오케이. 민영 학생, 오케이. 출석부에 체크할게요, 민영 학생. Okay, perfect answer. Thank you, 민영. Energy is released when surface area is decreased. So when you think about this droplet, right? When you have these two spheres with R, with whatever R, right? Okay. Okay. Right? We know the equation for their area and volume. We also know their equation for area and volume, right? When these two merge, okay? Let's say this is area and area 2. And when these two merge, we get new droplet here, right? Let's see, this is A3. Okay. When this happens, A1 plus A2 is higher than A3, right? So there is this decrease in surface area, which means there is decrease in surface tension or the energy per given unit area. Okay, so it takes up that amount of surface energy and induces this droplet movement. Okay, okay. So think about it. If the droplet is very small, micro-sized or nano, not nano, but like micro-sized, very small, right? Then this surface energy effect, or the surface tension effect, will be very, very big and nano, right? Okay, okay. So this animation here, okay, this animation, this single animation here explains what is happening, and probably this surface is rough because they are hydrophobic and maintaining this almost droplet structure. Okay? And back to the Hyunbin's question. His question was, sure, Sugato. Hyunbin's question was, hey, professor, in a CASI model, can we consider that that the air trapped between the nanostructures, what the surface does not get in that air gaps? Yes. 네. No, it does not get wet. 네, 젖지 않습니다. 네. 에어나 이런 데 있는 부분은 네. 오케이? 네. 잠시만요. 오케이? 여기만 젖는 거예요. 여기 애들은 젖지 않아요. 오케이? 그래서 네, 현빈 학생이 이해하고 있는 게 맞습니다. Okay? So the next question is the 현종. Okay? So professor, why is Young's equation reasonable in the case of nanoscale droplet? I'm asking it because I heard that its proof is based on macroscale case. Okay. Okay. Yeah. Okay. So, well, yeah. I mean, yeah. Maybe you have heard that Young's equation is not valid. It is only valid in macroscale case. But okay, maybe that is your information. Probably, maybe I'm wrong, but based on my knowledge, Young's equation is applicable, or Young's equation can be used in all length scale. Okay, and actually, the droplet to have nanoscale is really hard. But anyways, from my knowledge, Young's equation is valid for also for nanoscale, right? However, I think what you meant, Hyungjong, is that this surface effect or the surface roughness effect becomes much more important for nanoscale droplets. All right, so maybe that is why that we have to consider this Cassie-Baxter model or the Wenzel model in nanoscale, not the actual Young's equation. 제가 뭐 한국말로 간단히 설명을 드리자면 제가 아는 한의 Young's equation은 나노스케일에서도 쓸 수 있다고는 저는 알고 있는데 저희가 나노 사이즈로 오게 되면 드럼렛이 나노 사이즈면은 약간의 러프네스, 표면에 약간의 러프라든지 표면의 이런 계면의 이런 특성에 너무 의존성이 커지기 때문에 기존의 영스 이퀘이션 막 물방울이 진짜 커요. 물방울이 막 한 바켓이야. 그러면은 I mean yeah, but like what I'm saying is that no, Cherish, I think Hyunjong is trying to say in a large scale, right? Like the droplet that we can see, right? Okay, 네, 제가 아까 설명을 하다 말았는데 이게 조금 뒤죽박죽이네요. 네, 좋습니다. 근데 물방울이 굉장히 크면 표면이 러프해도 그죠? 물방울이 되게 크면 그죠? 표면이 어느 정도 러프해도 물방울 전체의 인터널이라든가 그죠? 아니면은 중력의 영향에 의해서 사이사이 물방울들이 잘 들어갈 수도 있고요. 오케이? 근데 물방울이 굉장히 작아지면 굉장히 작은 사이즈의 러프니스에 따라 의해서도 젖는 비헤이비어가 달라지기 때문에 네, 그러한 물방울 차이에 따른 표면 구조와의 그런 상관관계 그런 거에 따른 차이는 있을 것 같습니다. 제가 틀릴 수도 있지만 제가 이해하기로는 그래요. And Cherish, yeah, you're right. Outlets are inherently not macro scale, right? Macro is like in the order of um, macro is like in the order of meters, right? Tens of centimeters, right? I mean, if 현종, maybe it's better to say meso가 맞을까요? Meso scale, right? In the order of millimeter to centimeter scale. There are droplets in meso scale, right? Okay, so perhaps that's the case. Okay. Sure. So this is the worst, the biggest thing I hate about this online lecture is that it is really hard to deliver, or it is really hard to have quality, good quality discussion, right? 그렇죠? 지금만 봐도 굉장히 지금 많은 이러한 좋은, right? We just had really good discussion about this topic, but I mean, I believe you guys will have much better understanding if you can see my motion, my face, my facial expression, and also I'll have the same idea, right? I can tell whether students have understood or not by seeing their faces, right? But it is really sad that I can't. So, okay. Alright. Okay. 지금 다음 토픽으로 넘어가기 전에, so we have about 10 minutes left, but I wanted to have a very short break. So while we are taking break, you can go to restroom or you can watch your music video or whatever, but we'll take a break about 2 minutes. So in the meantime, I'll just do some regular chat. So, so I believe all graduate students are in campus, right? 혹시 대학원생인데 학교가 아니신 분? Right? Okay. Good. But I believe that many of the undergraduate students are off campus. 혹시 학부생이신데 학교신 분? 학부생이신데 학교신 분? 아무도 없어요? 손 들고 있구나. 아, 네. 은주 학생, 수정 학생. 세연 학생은 학교에서 뭐 해요? 네. 네. 박소 교수님이 잘 챙겨주시죠? 네네. 네. 지은 학생은 4학년, 3, 4학년, 지은 학생 두 분 다 학교에 계시네요. 네. 오케이. 오케이. 그러면은 학교에 안 계신 학부생분들은 어디서 수업 들으세요, 지금? 자기 집이다. 나 지금 집이다. 네. 오케이. 집 아니신 분 어딘지 한번 얘기해 줄래요? 다 집인가 보네요. 오케이. 네. 알겠습니다. 오케이. 그럼 지금 뭐 누워있는 분, 나 지금 누워있다. 누워서 핸드폰으로 수업 듣고 있다. 손. 인성 학생, 지은 학생, 승훈 학생이 누워서 듣고 있는 거예요, 지금? 아니, 뭐 뭐라고 하려는 건 아니고 궁금해서. 네. 알겠습니다. Okay. Okay. All right. So I don't have that many time left, but yeah, I'll get back to the lecture. So yeah. Another example that I wanted to talk today. Perhaps I'm running out of time, so I have to continue on Thursday. But I wanted to talk about heat. Okay. So heat. So heat is a form of energy, right? Okay. And heat, right, is basically what is a form of internal energy, right? So every system has its own internal energy at atomic level. And when we convert that energy, right, and when we quantify it, we can quantify in temperature. Okay. Okay. So that is heat, right? 그래서 열, 한국말로 하면 열이죠, 열. Okay, 열, right? So there are a large field where people use these heat and do the engineering, right? So thermal engineering is controlling heating or cooling processes in an enclosed environment or an open environment using various equipment. It involves the science of thermodynamics, fluid mechanics, heat and mass transfer. So all these fields are core courses in mechanical engineering. 연력학, 유체역학, 열전달, 그죠? Okay. One of the most obvious example in summer is air conditioning. It composes compressor, condenser, evaporator, coil insulation. So when we think about a house, right? When we think about a system, right? 공조 시스템, 그죠? 냉난방, 그죠? 이러한 모든 것들에 thermal engineering 들어갑니다. The another example that we can think of is electronics cooling. Right? Again, the heat, right, can be a problem in any high performance system. The higher speed processors normally consume more power and therefore generate more heat. 그래서 뭐 굳이 얘기하자면은 발열, generation of heat generation. Okay. Okay. The processor is usually the single most power-hungry chip in a system. Which power-hungry라는 말은 it consumes a lot of power. That means it is power-hungry, right? So there are systems that consumes a lot of power, right? Which means that it takes up a lot of battery life. Okay. But sadly, a lot of this power from battery is being wasted as heat. 죄송해요. 이게 태블릿이 그러니까 얘네가 자꾸 열로, 그죠? 열로, 발열로 에너지가 소비되는 거예요. 그죠? 그래서 뭐 배터리나 전력으로도 안 좋고, 또 온도가 높아지면 as the temperature goes up, the efficiency of this chip drops, or in a worst case, there can be explosion like this. 그죠? Samsung Galaxy Note had this issue of explosion, and it was because of the localized heating. 한국말로 하면은 뭐 국소 발열. Okay, all right. And also, people gather this solar energy harvesting, right? People receive this sunlight, right, and have these solar panel structure using the semiconducting material, right, and using this, what the current effect, or optoelectric, we are converting this optical to electrical energy. Right? That is the concept of this solar energy harvesting. And the sunlight is also another form of heat. This is radiative heat. 한국말로 하면은 옥사열. Okay? Right? So there are so many cases where we utilize this heat. Right? So when we talk about heat, right, the concept of heat is that all these heat is being transferred. Okay? So what I'm trying to say here is that when there is a temperature difference, when something is hot and something is cold, there is this directional flow of heat. Okay? And there are the very wide range of heat transfer mechanism, such as conduction, convection, radiation, phase changes. 뭐 한국말로 굳이 하자면은 뭐 전도, 대류, 복사, phase change, I'm not quite sure, but what I'm saying is that usually the heat flows from hot to cold. Okay, so there is this direction. Okay. And depending on the material, right, metal has high K, which is thermal conductivity. Right? Glass has low K, right? So the rate of heat being transferred is low. For metal, is very fast or very high, right? Oops, I'm sorry. So there is this behavior of many material when there is a large temperature difference is present. Okay? So in nanoscale, this kind of heat transfer or this kind of a thermal effect changes dramatically. And that is what we are going to learn in next lecture. So that is actually what we are going to do. Right? And I have a very short announcement, right? So there is a reading assignment, right? I believe all of you know where this textbook is. I uploaded the PDF file, right? Please do not share this PDF with your friends who's not taking this class. Okay, just keep to your just keep inside of your computer. Right? There is a chapter 2 called Quantum Mechanics. Please read this chapter as much as you can. Until next Tuesday, okay? Okay, because we'll talk about some of these quantum mechanics for about 30 minutes on Thursday and more on next week. So please read this chapter of this book, read this chapter as much as you can. So that'll be it, and we will again come back to this nanoscale heat phenomena during during the next lecture. Okay. All right. So I believe there was one comment. Let me see. Okay, so yes, professor. Okay. So 네, 그러면은 I think that's it for today. Thank you all for your time, and I hope you have a great Tuesday. And again, stay healthy and have a good rest. 네. 그럼 뭐 잘 먹고 쉬시고 안전하게 잘 지내시기 바랍니다. 혹시 뭐 수업 끝나기 전에 하실 말씀 있나요? 네, 없으면 강의 오늘 여기까지 하겠습니다. 다들 고생 많이 하셨습니다. Alright, I'll see you guys on Thursday. Bye bye.